engineering. It's really our pleasure to have all of you here despite the weather. Every time we have special weather, we have a special guest. So today we have a very special guest. But I will pass to our icon co-director or one of the co-directors, Shreyas Mo, to introduce our speaker today.
Thank you. Uh, Welcome all to our seminar, excellent seminar, and also thank our seminar organizer Zira and thank you. And this. Yeah, today we have a very special speaker and leadership and also excellent research. Actually, I Professor Shreyas Sundaram. We could at the Institute for Control Communication Networks. Actually, I haven't known, started known Shreyas research when I was a PhD student. But we worked on the same area on multi system and kinesis. And then after joining Purdue, she has helped me a lot during my assistant professorship years. So thank you very much. I want to thank you, Shreya. So a little bit about Shreya.
You can skip, no problem. Yeah, we can get into it.
Yeah, Shreya is a marine governance professor in the ECE, and his research, they about coordination, optimization, and testing for clusters.
Perfect. Yeah, thanks, Harsha. Yeah, thanks for pleasure to give a seminar as part of our series. It's been great to hear what everybody has been working on both internally and externally, right? And often we find out about stuff that other people in other groups are doing or other people in other universities are doing. We don't often find out or have the opportunity to talk about stuff we do. So it's I'm really pleased to be invited. Thanks for doing that. So the goal today is to provide an overview of stuff that we've been working on over the past, 10, 15 years or so, pertaining to resilient distributed coordination and networks. And so the talk is really meant to be a tutorial. Okay, so it's meant to give an overview, teach you about some of the relevant concepts that we've identified. And so if you have any questions at all as we're going, please let me know. Really, the concept should be embarrassingly simple. Okay, that's the goal. All right, so what's the general setting? Well, we're looking at these problems of coordination and estimation and learning, let's say, in general, in these large-scale networks. So, these large-scale networks show up everywhere, right? So you might have autonomous teams of robots that are monitoring a given environment or cooperatively trying to achieve a certain task. You may have smart factories where you've got sensors and actuators that are spread out throughout the environment, trying to work together to achieve some manufacturing goal. Smart cities, for sure. You've got, commuters and cars and airplanes and sensing networks spread out all throughout, and even social networks where you've got people which are forming the network. Okay, and in all of these cases, the idea is that you've got all these sensors or elements that can interact with the world in different ways. They have access to different information potentially. And these networks themselves could also be changing over time. The agents could be moving, these connection links could be intermittent, right, going up and down. And furthermore, one of the key parts of this talk is going to be what happens if you have certain nodes in the network that don't follow the algorithms you expect them to follow, okay? Because they could be adversarial, they could be compromised, faulty, etc. So overall, the objectives in these settings is to formulate algorithms for these network systems that allow all the regular nodes, right, the nodes that actually are doing what they're supposed to be doing, to work together to achieve whatever objective they're supposed to achieve, despite the actions of the bad guys in the network. How do we think about the relationship between the network structure and the objectives and the algorithms? That's really the key here. So there are very specific instances of these problems that show up in practice. Here are just a couple, examples. The distributed consensus problem is sort of the baby problem that everybody starts out with, right? It's a nice problem because it's got a nice structure. You can also gain a lot of insights. So I'll start out by describing that problem. I'll talk a little bit about distributed optimization, not much, because some of these insights pertaining to the kinds of things I'm interested in will translate directly to distributed optimization. And then I'll end up with some hypothesis testing and learning type of problems as well. Okay. So let's start with the very simple setup here. So again, this is for people who may not have seen anything to do with distributed algorithms before, but just to introduce the key ideas, we'll quickly move into some of these aspects of resilience. So the distributed consensus problems is the following problem. You've got some sort of network, right? So you got a bunch of nodes and you've got edges between the nodes indicating information exchange capabilities. Okay, so now these nodes could represent anything, right? Computers, sensors, robots, people, depends on the context. Now, suppose that each node in this network has access to some initial value, right? Let's think about it in terms of opinion dynamics. It's easy to kind of imagine that. Everybody in this room is a node in the network. You can talk to the people to the left and to the right and maybe directly behind you. And you all have an opinion on a certain topic, right? Do you like cake or ice cream? Pick a number between 0 and 10. 0 is cake, 10 is ice cream, right? So each person has a number. And you'd like to come to a consensus on the average rating, right? What does the average kind of liking, the preference in this room come to? So we'd like to find the average of all the numbers in the network. So how could we do that? Well, a simple thing would be everybody just shouts out their number and I sit at the front and I note it all down and compute the average. But that'd be a centralized way to do it. Well, we don't want to do that in a centralized way. We'd like to do it in a distributed way where people kind of talk to each other over time and change their opinions or update their opinions over time. And hopefully over time, everybody comes to an agreement about the average value, right? So that's kind of the consensus problem. Okay, there are a variety of ways to solve this problem. Here's a very simple approach. What happens if at each time step t, so imagine t is some increment, right? Every minute, every hour, every day, whatever it is, each of you talks to your neighbors, right? The people that you that are near you in this network. You look at what their current value is, and you average that with amongst themselves and with your own value. So this WIA, WIJ is just a weighted linear combination. You can just think of this as averaging your value with your neighbor's values. Okay, everybody in the network does this. So you can imagine what would happen if everybody kept averaging their values of their neighbors. Every time I average, I'm getting closer to my neighbor's values. And over time, as long as the network is connected, it's fairly easy to prove that everybody will in fact converge to the same value. And that value is going to be a convex combination of the initialized. It may not be the exact average, but it will become weighted average. Okay, that's great. So you can run this, this kind of has a common application at flocking. If the value corresponds to the direction that you all want to head in, so they all start out in some random directions, they do some averaging and they all converge to the same value. Okay, so very simple, algorithm. Hopefully you can see why this might work. All right, what happens if there's nodes that don't average? What happens if there's somebody in the network that says, I don't want to listen to other people, right? There's always stubborn people in every society, right? In every friendship circle. So on the left is what happens if everybody averages. Everybody does convert to some, intermediate value. But if there's even one node in the network that decides it's not going to change its value, right? We can keep its values fixed at some stubborn value. You can easily show that as long as the network is connected, everybody else will eventually converge to the value of the stubborn node. Okay, so this sort of stubborn individual can easily corrupt this entire network and draw everybody's values to them. Okay, that may be good if the stubborn person is actually correct, right? And they have strong opinions, but they're correct opinions. You want to be able to influence society, but it's bad if this person doesn't have correct opinions, right? And yet everybody else is acting in good faith. A single stubborn node can compromise this entire network. Okay, so that doesn't seem great. So what do you do when you have potential nodes in the network that don't follow these algorithms, right? You can think of them as adversaries, and I'll talk about different adversary models soon. But this kind of problem has been looked at in a lot of communities for decades, okay? So essentially in computer science, this goes back to the 1980s under the name of Byzantine consensus problem. Okay, control systems and communications folks have been looking at this for about 20 years now. Okay, so starting back in the mid 2000s, and then sociology and economics, as you might imagine, this plays a key role in those settings as well, right? Obviously, you want to understand how social networks form and how people, buy products, change their opinions about products, things like that. So there's some key insights that come from a lot of the early work on this topic. Okay, so before I get into that, let's talk about what we mean by resilient algorithms. So when we say, oh, I want to make a resilient algorithm, and resilience is a kind of a popular word these days, the first question anybody should ask is, what do you mean by resilient, right? So you shouldn't just say, oh, that's a cool resilient algorithm. You could say, what do you mean that's resilient? What are you resilient to? So there are a few key questions that I think, after working on this for couple decades, these are key questions that I think are important, right, to ask. So the first is the normal nodes, the nodes that, follow whatever algorithm you want them to follow. What do they know? What do you want them to know about the network? Do you want them to know the entire network topology, or do you want them only to be aware of their local neighborhoods? Do you want them to know what everybody else is supposed to be doing, or do you want them to only know what they themselves are supposed to be doing? right? So how much power do you give them in terms of information is going to determine how much misbehavior they can tolerate. How about computation and storage? How much computation and storage do you want the normal nodes to have? A lot, right? Do you want them to be able to gather all the data they've ever seen and do a lot of computation on it? Or do you want them to do very simple computations on very limited data? What are the objectives, right? What do you want the good nodes to be able to achieve? Do you want them to get the desired objective exactly, the thing that they're supposed to be doing if there are no bad guys? Or are you willing to tolerate some deviation from that because you have to tolerate misbehavior? These are some questions you have to ask. Furthermore, in terms of the bad guys themselves, what kinds of misbehavior do you want to be resilient to, right? The first is, do you want to tolerate nodes that just drop out of the network, right? They just stop working, their battery runs out. In that case, these are sometimes called crashes. Or maybe you're looking at nodes that are faulty in some sort of modeled manner, right? They inject noise into the system or something. They're not trying to be mean to you or, malicious in a specific way. They're just doing crazy things because they're malfunctioning. Those sometimes come under the umbrella of faulty nodes, okay? But then if you have more carefully chosen misbehavior, they're actively trying to mess up your network, then you have to think about them differently. So nodes can potentially update their states in arbitrary but unknown manners. So sometimes those are called malicious nodes. And if nodes can send conflicting values to different neighbors, right? I tell you one thing and I tell somebody else something else, that's an even stronger model called Byzantine nodes. Okay, that's what the bad guys do. What about the number of bad guys you want to tolerate, right? So that could also make a big difference. There's F total models. So that says up to F bad guys in the entire network, or F local models, which says up to F bad guys in the neighborhood of every good node. Okay, as you can imagine, F local is a much tougher problem, right? Because you can have potentially a lot of bad guys in the network, not just F. So when you ask all these questions, you can then start talking about resilience with regard to the specific assumptions you've made about each of these kinds of things. Okay, so let's gain some insights about some of these classical kind of results back from the computer science literatures, right? So let's look at this very simple network right here. So you've got 4 nodes, and suppose node 2 is malicious, okay? It's going to lie. And suppose node 1 wants to know what node 3's value is. Okay, node 3's value is 7 in this case. Now, how can information from node 3 get to node 1? Well, there's only 2 ways for that information to flow, through node 2 or through node 4. Now, if node 2 doesn't want node 1 to know node 3's value, suppose node 2 pretends that node 3's value is 9 instead of 7, okay? Now, node 1 is going to be sitting there, and all information from node 2 is going to be consistent with node 3's value being 9. All information from node 4 is going to be consistent with node 3's value being 7. How is node 1 going to decide which one is lying, right? It could be that node 4 is lying and node 3's value is actually 9. So the problem in this network is that although there's multiple ways for information to flow, there isn't enough multiple ways. There isn't enough redundancy in the information flow for this to make a decision about what the correct value was, right? So in this case, a single bad guy is able to prevent certain nodes in the network from recovering the truth about other values in the network. So what we really need is a tiebreaker, right? We need more paths in this network. So this goes back then to this very fundamental notion in resilience called graph connectivity. So connectivity of a network is the smallest number of nodes that you have to remove to disconnect the graph. Okay, so in this case, if I give you this graph, what's the smallest number of nodes I have to remove to disconnect the graph? 1, right? If I remove this node, these nodes are isolated. In this graph, the smallest number of nodes I have to remove is 2, right? Because if I remove any single one, there's still a path between all the remaining nodes. In this graph, the smallest number of nodes is 3, okay? So the set of smallest nodes that you have to remove to disconnect the graph is called a vertex cut. Now, there's this very classical result in Menger's theorem, in graph theory called Menger's theorem, which says that the connectivity of the graph is also equal to the number of disjoint paths in the network between any pairs of nodes. So for example, here, the connectivity is 2. That means that if you pick any 2 nodes, there's going to be 2 disjoint paths to go between those pairs of nodes. In this case, the connectivity is 3, so there's 3 disjoint paths between any pair of nodes, okay? So as you can imagine, based on our thought experiment from a previous slide, the more disjoint paths, the better. And it turns out that there's this classical result that says if there's F malicious nodes, all the other nodes can reliably exchange information if the network has 2F plus 1 connected, okay? Because 2F plus 1 connected means there's 2F plus 1 different paths in the network between any pair of nodes. I just send the same value along those two f+1 different paths. At most, f of those paths are compromised by bad guys. f+1 of the paths are going to agree. I just majority vote. I got the correct answer. Okay. So computer science literature. Then back in my PhD, essentially, I was able to show that this connects to linear systems dynamics and control systems concepts called non-minimum phase zeros and so forth. And people have built on it since then. Now, the typical assumptions, though, when you use this fundamental result, is that all the good guys know the entire network topology and the nominal dynamics of the other nodes, right? So if I'm supposed to be able to leverage these different paths, I need to know how to send it along those different paths. And I need to know, I'm going to wait for information from Bob, and I'm going to majority vote on it. That means I need to know there's somebody called Bob in the networks, right? So this is not very scalable, but it does provide this kind of key fundamental lower bound of achievable performance when you have a network. So what we really would like is scalable resilient algorithms, right? How do we scale algorithms to millions of nodes, city scale, global scale, right? Swarms where things are coming and going, the network's changing over time. I don't want to know the identities of other nodes. I just want very simple local algorithms. So how do we think about what the requirements are in this? So let's talk about a very simple class of local filtering dynamics for consensus. Okay, and as we go, if you have any questions, feel free to put up your hand and ask them. So let's revisit this very simple algorithm. Remember what we said? We're going to just take our neighbors' values and average them and update our value to be that average. Okay, well, I have crazy friends, right? So I have an opinion. I'm willing to change my opinion. So I talk to my neighbors, my friends every day. I get their opinion on stuff, and maybe I'll average my friends' opinions. But I also have crazy friends, and I know they're crazy, right? Or I think they're crazy in certain ways. So I don't average everybody. If I have friends with very extreme opinions on certain topics, I'm going to like, thanks for telling me, I'm going to not listen to you, right, on that topic. So what happens if you do the following? Suppose I know I have up to F kind of crazy friends. So at each time step, what I do is I grab my neighbor's opinions, my friend's opinions, I remove the highest F and the lowest F. Okay, so I filter out the most extreme values and I just average the rest. Okay, very simple algorithm, right? So just taking all those values, removing the F highest, F lowest, and averaging the rest. Nothing's changing about the algorithm other than the set of neighbors that you're averaging. So remember, when I averaged everybody's opinions, all that I needed was for the graph to be connected in order for us to reach consensus. So now the key question is, what is the condition on the new graph? Or what is the new condition that's required for this thing to converge? Okay, so we started with this algorithm, and then I said, okay, let's think about, coming up with a graph where we might run into trouble. So imagine you have a network that looks like this, okay? So you've got a fully connected subgraph here. Everybody here can talk to everybody else. Okay, there's n over 2 nodes here, n over 2 nodes here. Everybody can talk to everybody else. So really two tight-knit communities, right? Everybody's a family here, everybody's family here. And every node here has exactly one friend in the other set, okay? Now, suppose everybody here has an initial opinion of 0. Everybody here has an initial opinion of 1. And everybody's going to follow the algorithm I just mentioned, where they're going to throw away one highest and one lowest value at each time step, and they're going to average the rest. So what's going to happen? So essentially, this node, let's look at that one. It looks at all its neighbors. It sees 0, 0, 0, 0, 1. Throws away the highest. It's going to throw away 1. Might throw away 0. And averages the rest. Its value is going to stay at 0, right? So everybody here is going to stay 0. Everybody here is going to stay 1. No consensus reached in this network. Right? This is a beautiful network from the perspective of the connectivity metric. You'd have to remove half the nodes in this network to cause this network to fall apart. So you could potentially tolerate n over 2 bad guys in this network if every node knew the entire network. But just a simple algorithm where I'm just throwing away highest and lowest and averaging the rest is preventing consensus even when there are no bad guys in this network. Right? So this algorithm seems awful. So then we said, okay, well, are there conditions on the graph under which it will converge, right? This graph clearly shows it's going to be tougher for this algorithm to converge. So why did consensus fail in this network? Well, consensus failed in this network because we were able to take this network, break it into 2 sets where no node in any set was using information from a node outside its own set. Each node was throwing away the only useful information it was getting from outside its own set. That was because in this network, no node in any of these sets had enough neighbors outside its own sets, right? Because the filtering was causing it to throw away all its edges. So what we need is a new topological property to characterize conditions under which this kind of algorithm will succeed. Okay, that's really what this is pointing to. So that's what we did. So we created a set of new definitions for networks. So I'm going to introduce those definitions with these examples. So suppose I give you a graph and I give you a set of nodes. I give you a number R. I'm going to say a set of nodes is R reachable if that set has a node that has at least R neighbors outside that set. Okay, so let's do an example here. So this green set right here is 3 reachable because it's got at least one node that has at least 3 neighbors outside. For example, D5 has 3 neighbors outside that set, right? Similarly, this set, peach or pink or whatever this is 4 reachable because it's got a node that has 4 neighbors outside that set. Okay, so this R reachable property is on a set. What I want is a graph property. So then we say a graph is R robust if for every pair of disjoint subsets of nodes, at least one of the sets is R reachable. Okay, so what does that mean? So essentially, no matter how I pick 2 disjoint subsets of nodes, at least one of those sets is going to have a node that has R neighbors outside. If that's true, regardless of how I choose pairs of subsets of nodes, this graph is said to be R robust. Okay, and you can check in this graph, no matter how I do this, right? At least one of the sets is going to be R reachable. Why is this property useful? Because remember, in that counterexample graph we showed, we were able to find 2 subsets of nodes where neither subset had a node that had more than one neighbor outside, right? That was causing the whole problem. So this is what's going to save us from this. Is the definition clear? Okay. So then this ends up being the key property. So remember, connectivity was the key property when you knew everything about the network, but for this simple local filtering algorithm, if the network is 2f plus 1 robust, then you can show all the good guys, all the normal nodes, will reach consensus in the convex hull of their initial values, despite the actions of any f local set of Byzantine nodes. Okay, so the worst possible behavior is allowed here, f local, so huge numbers of bad guys in the network. Okay, and this is using that very simple scalable algorithm. Okay, so the price you're paying is essentially you're paying more. This is a stronger condition than 2f plus 1 connected. And you're giving up also exact consensus on the average. You're only guaranteeing that they're going to reach a value that's between the highest value of any good guy and the lowest value of any good guy. Okay, so you're paying certain prices, but you are getting a lot in return. Okay, so the key takeaway point here is that this graph satisfies this required robustness property. This very basic, simple algorithm gives you this nice resilience guarantee, okay? There is a negative result that it's hard to check if a given graph is R robust. If I walk up to the graph and say, is this R robust? There's no known polynomial time algorithm to solve that problem. Okay, so here's kind of a visual interpretation of what's happening, right? So the bold is what the bad guys are doing. Essentially, the bad guys' behavior will be constrained to lie between the good guys' values, because if they go above or below those values, they're just going to get thrown away, right? And so essentially, the bad guys, fine, they can try and do some manipulation, but they're going to get squeezed out over time. They're very intuitive. So the nice thing about this local filtering approach and the associated robustness property is that essentially it becomes a plug and play type of condition, right? So if you want resilience in some distributed algorithm and you're using some sort of like consensus type thing, right, where you're averaging stuff, if you wanted to make it resilient, you could essentially just plug this in. Now, the analysis and the proofs takes work, right, because it depends specifically on the algorithms you're looking at, but this ends up giving you a nice first tool to be able to analyze the problem. So distributed optimization, or as I gather from my colleagues, this is also called decentralized federated learning, is that each node has a function in this network. It may be a function of some data it's gathered. The nodes want to cooperatively find the minimizer of the sum of their functions. And so, there's standard kind of consensus plus gradient step algorithms that do this. Well, this is a consensus problem. You've got an averaging. You want to make it resilient. Just replace this with the local filtering and go. Okay, and so you can get exactly the same results, which is if the network has the required robustness properties, the step sizes satisfy certain conditions, all the good guys will reach consensus and their consensus value will be similar to the optimization value. Yeah.
Are these adversaries assumed to be knowledgeable of each other and working together?
Byzantine nodes are amazingly powerful. They know each other. They know the values of all the good guys. They know all the information transmitted in the network. They can coordinate with each other. Yes. Yeah.
Is their most powerful like distribution within the network? Is it typically when they're all grouped together or
Great
when they're
question.
distributed?
Yeah, that's a tough question to answer. Yeah, it's unclear. The adversary can also choose, the adversary is allowed to have unbounded power to also choose the locations of the bad guys. Yeah.
Sure.
Yes. Yes.
For this is more like the cancer of class reading distance.
Correct.
So what if we keep our cancer by fusion readings? So it
Yep.
can still work. The same.
It should still work. Yeah, I mean, fusing gradients meaning some sort of averaging on the gradients, right?
Yeah.
Yeah, exactly. So you could, the analysis will change, but definitely you could throw away highest and lowest gradients as well. There are some complexities, right? So when you have multi-dimensional functions, so right here, when I say gather all my neighbors, estimates of the optimizer and then throw away highest and lowest. Now, if I have multiple things that I'm getting from neighbors, there's some complexity. I mean, so Shreyas and I and the students have worked on vector consensus type problems, right? So how do you throw away highest and lowest in a vector setting? What does it mean to say one vector is higher than another vector? Different components could have different values, right? And so if you actually want to satisfy certain conditions, like the value you're computing is inside the convex hull of something, it can be very, very complicated to do that. However, you can also imagine simpler algorithms where you're just doing component-wise extreme filtering. And in those cases, it's much simpler. So each one of them has its own little, let's say, unique characteristics. Okay, so one quick thing here I wanted to mention was, I talked about this robustness property, and I showed you this example of this graph, which seemed like was beautiful from a traditional perspective, right? The connectivity perspective, but this kind of filtering algorithm didn't work on that graph, even when there are no bad guys. So you could say, fine, you're telling me if the graph is 2f plus 1 robust, this algorithm will work. This seems like a terrible condition, like it's never going to work, right? So it's like saying if cows could fly, your algorithm will work. Well, fine, thanks for telling me, right? Well, so the key question we were asking was, are there reasonable networks where this kind of robustness condition holds? And one model for large-scale networks, or one way to think about large-scale networks is through the framework of random graphs, right? So essentially, we carefully came up with that counterexample graph to try and illustrate the point or to think through the conditions of your part. But if I were to randomly generate a graph, and randomly is in quotes here because there's many ways to do random, what would, do those resulting graphs have these properties? And this was a beautiful kind of result, at least to me, was that if you were to look at these common models for large-scale random graphs, you get this amazing property that our robustness and our connectivity, which are nominally very different properties, this is much stronger than this one, they coincide in these random graph models, meaning that at certain thresholds, these graph models are connected, but then at the same time, they also become robust. So there's this beautiful hidden structure in these graphs, which will facilitate then exactly these local filtering algorithms to be run on these large scale networks, right? So there's lots of people that followed up on that work and showed that the same properties hold in all sorts of other interesting graphs. I've worked with Jay Kamara at UPenn to come up with formation control algorithms to guarantee that swarms have these properties and so forth. So the main thing to take away here is local filtering is a very promising scalable mechanism for resilience and coordination. Okay, so I just wanted to summarize this first part of the talk, which is if you're going to talk about resilience, you got to first think about what you want to be resilient to. Then you got to think about the relationship between the network topology and the algorithm. And so if you're thinking about scalable algorithms, this robustness property seems to be critical. And then one thing to emphasize is that all the problems that I've talked about so far, consensus, optimization, etc., have had the feature where every node in the network has useful information, right? In the consensus problem, every one of us has an opinion. In the optimization problem, every one of us has a function, okay? What happens in settings where different nodes have different types of information, right? So the sensors that are located in one part of the network are able to sense something. We're going to look at that next. So I'm going to pause there for a second to see if anybody has any questions on this first part.
Yeah, so quick question on the idea of learning consensus. So you mentioned that the strategy that you took was picking out highest and lowest and depending on the kind of graph. Would you say that guaranteeing that you will reach a consensus and not just a value within like a context goal? Would you say it's kind of like a no free lunch situation where you're not really like, you know, if you're able to identify which agents are truly malicious, you're not going to be able to get to the consensus or vice versa.
Exactly. So let's try a simple experiment. Okay. So you pick a number in your head between 0 and 10, an integer. Okay. And I'll pick a number between 0 and 10, an integer. Okay. And let's suppose that we want to calculate the average of our values. Okay. How would we do that? Well, whatever algorithm you want to do, maybe you report your value to somebody, I report my value to somebody, we tell each other values. Who's to know what my true value is, right? And so maybe I say my number is 9. Okay, was it a 9? Or am I just trying to bias the average up, right? Maybe the true value that I actually sensed was a 0. How will you ever know whether I truly got a value of 9 or whether, I got a value of 0 and I'm biasing towards 9? Impossible, right? Fundamentally impossible. So the fundamental result that ends up coming out here is that it is not possible. There are no algorithms that allow you to calculate the true average or calculate the true minimizer of a set of functions under the Byzantine model, because the Byzantine model allows the bad guys to do arbitrarily anything. If there's correlation between values, so if I know whenever you pick a 0, my value is going to, or whatever value you get, my value has to be between 2 of those. Then if you get a 0 and I get a 9, one of us is lying, right? But if there's no correlation like that, it's impossible. Yeah, yeah.
I'm wondering, like, if you look at adversarial agents,
yes.
So we are calling them adversarial agents because they're not following the dynamics that we have written down.
Yes.
So basically, they are following some other dynamics that we do not know.
Correct.
For example, if say that all adversarial agents follow, if we assume that they follow a certain dynamics,
yes.
So that dynamics.
Yes.
Then is it possible to see how the graph goes?
Sure.
Because okay, one approach is that they are generating random values.
Yeah.
That could be they are following some deterministic model.
Correct. So if a node updates its state according to a known model, we typically call that faulty. Yeah. So definitely the conditions will be very different. Yeah, exactly. So if you can predict how the bad guy is going to behave, good. Yeah, go for it. You should, right? There's no reason. So this could be a very conservative result. If you know the only thing that's going to happen in your network is the battery runs out, don't use the Byzantine model, right? Because there's no reason to do that. You're just going to not get values from people, but you're throwing your values for no reason. But if you don't know that, and you better justify to whoever's paying you the money to design the system that this is the only reason, this is the only kind of model you to care about. If you don't know and you want to tell them, look, I want to be extra careful, I'm assuming this, but this is the price you're going to pay, it's all a trade-off. Yeah, no free lunch.
And I got another idea.
Yeah.
So like, if you have plot the values of all the graph of there, right?
Yeah.
So they were all varying with respect to time.
Yes.
Now, basically, just by looking at this graph, now I can tell that which nodes are malicious, which are not.
Who's looking at this graph?
Okay, say like after running certain time.
Yeah.
So we do have a record of all the values. Right?
But who's we?
Like there will be some sensors or something in the head.
Yeah, yeah. Everybody else only access to what they see and their neighbor's information, right? They don't get to see this big picture. And so they may see somebody acting erratically next to them, potentially, yeah. But then are they acting erratically because their neighbors were acting erratically? Maybe they're averaging properly, right? And maybe they're throwing their values, but one of the values that, like a bunch of the values that they're getting may be erratic. So you don't know what the neighbors are doing. And so it's hard to then say, you're being crazy. Well, he could say, I'm being crazy because my friends are being crazy. What am I supposed to do, right? So it becomes tricky, but certainly under different assumptions, you can maybe dig into it for sure. Nothing comes for free, unfortunately. So let me get into distributed hypothesis testing, right? So this is a kind of an example of a problem where you've got nodes that are getting information from outside the network, and we want to see how to do this. Okay, so here's the setting. Okay, so we live in a world, okay, we're in some environment, and there's m possible states of the world. So there's m possible things that could be true. One of them is true. Okay, so the true state of the world is denoted theta star. Okay, we don't know which of these is the true state of the world. Now you've got a bunch of agents in a network, and each agent in this network receives certain private signals. Okay, so at each time step, it's got a sensor, and that sensor is going to be spitting out values to that agent. And the values of that agent are going to follow a random distribution, but the distribution is conditioned on what the true state of the world is. Okay, so depending on what the true state of the world is, the distribution of signals sensed by that sensor are going to be different. Okay, so for each hypothesis theta, each agent has a conditional likelihood function. So what does this mean? This function is basically just saying, what is the probability I'll see a value of Wi in my sense signal if theta were the true state of the world? Okay, so this is just a sensor characterization, right? So if it's a red light, here's what my camera is going to be, the distribution of signals I'm going to see from my camera. If it's a green light, here's the distribution of signal I'm going to see from my camera, etc. So we assume that this is known. Now, each agent in the network wants to determine what the true state of the world is. Okay, so what it's going to do is it's going to maintain a belief over these M hypotheses. So that belief is just a probability that theta 1 is true, theta 2 is true, theta M is true, okay, which is going to update over time based on information that it gets from its neighbors and from its own signals. Okay, is the setting clear? Okay, so we're all just trying to figure out what's true. We're getting measurements. We know what distributions we'd be getting under each of those hypotheses. We want to figure out how to learn the true state of the world. So we'd like to come up with rules that guarantee that the belief of each agent I on the true state goes to 1, right? And the belief of each agent I on all the other states goes to 0 asymptotically, almost surely. So here's a simple example. For example, you've got a bunch of nodes that are spread out in some environment, and they're trying to do some sort of classification task, right? So you've got some targets that are spread out. Maybe the locations of the targets are not known, or the types of the targets are not known, but maybe these are drawn from some finite set of candidate hypotheses, right? Is it a drone? Is it a kite? Is it a bird? Is it something else? Is it located in segment 1, 2, 3, 4, etc.? So that would be an example of this problem we just looked at. Okay, so, I'll talk about some contributions with regard to this problem. Like bad guys haven't shown up yet, but even before that, I think there's some interesting insights to be gained here. So I'm going to talk about a new distributed learning rule or hypothesis testing rule for this problem. I'll talk about how this is embarrassingly simple, this problem, right? I hope to convince you that this is embarrassingly simple. And then I'll talk about its extension to bad guys in the network. So let's do a simple example here, right? So just to lay out some of the terminology and concepts. So suppose you have a single agent and there are 3 possible hypotheses, theta 1, theta 2, or theta 3. Those are the only things that could be true. And the signal space of the agent is heads or tails. So its sensor can only spit out heads or tails or zeros or ones, however you like to think about it, okay? And suppose the signal structure of the agent is like this. So if the true state of the world was theta 1, it's going to see heads with probability 3/4 and tails with probability 1/4 at each time independently over time. Okay, similarly, if theta 2 were the true state, it's going to see heads and tails with equal probability. And the true state is theta 3, it's going to see heads 3/4, tails 1/4. Okay, so each row of this matrix right here is the likelihood function. Okay, so this is the likelihood function, which is a distribution of signal values given that theta 2 is the truth. So for example, let's just, do a simple example, right? So you flip a coin, one of these 3 things is true, right? And you see tails. What do you think? Let's say you had an equal distribution prior on theta 1, theta 2, theta 3. If you see a tails, is it more likely to be theta 1, theta 2, or theta 3? What do you think?
Theta 2.
Theta 2, right? Because it's probably pretty unlikely that you see theta. So maybe loosely speaking, I think it might be theta 2. Maybe you have some way of calculating the probability. I'll talk about that in a second. Then you flip again, and you see heads. Well, probably you're even more convinced that theta 2, right? Because you're probably seeing it half the time. Okay, flip it again. Okay, looking pretty good. Looks like theta 2. Oh, wait a minute. Right? So now you're starting to think maybe it's theta 1 or theta 3, right? So because now I'm seeing, if I run this thing long enough, I'm seeing heads about 3/4 of the time and tails 1/4 of the time. Could you tell whether it's theta 1 or theta 3 from this? No. So there's no way you could possibly distinguish between theta 1 and theta 3, okay? But you can distinguish between theta 2 and theta 1, theta 2 and theta 3, right? You're going to have pretty low belief that it's theta 2 after this string and pretty high belief at theta 1, theta 3. So some terminology here, based on the signal structure, theta 1 and theta 3 are said to be observationally equivalent. So from the observations you're seeing, you cannot distinguish between those 2 signals, between those 2 hypotheses based on your signals, okay? All right, so then you can throw some fancy looking stuff. This is the kind of stuff you'd show your friends if you want to impress them, right, with math, but there's nothing, I hate this notation. So there's a whole bunch of vertical lines here for no reason, but basically all this is doing, this is called the KL divergence. And all it does is it eats two distributions, right? This is the distribution of signals you'll see if theta under theta m. This is the distribution you'll see under theta n. So this function takes two distributions and it just spits out a number telling you how different those distributions are, right? There's a specific way to calculate that. That's all this complicated notation is. There's some nice features of this, which is that it's always non-negative and it's equal to 0 if and only if these distributions are exactly the same, okay? So from that perspective, we can say that two hypotheses are observationally equivalent from the perspective of agent I, if and only if the KL divergence between these two things is 0, or in other words, the distributions are exactly the same. Okay, so this, as you can imagine, the bigger this is, the better that agent can distinguish between theta m and theta n, right? So that's how the more different those signals are. Okay, so let's talk about some ways people have solved this problem. Okay, so in general, people have this tendency, natural tendency, correct, good tendency to basically say, if I have a distributed coordination problem, I should just use consensus, right? I should just average stuff. And it turns out that'll work. That'll work a lot of the time, okay? And so here's a very simple example of that. First is, okay, so this agent, I, at each time t, receives a signal si, or at time t plus 1, let's say, receives a signal si t plus 1, okay? So what should it do with that signal? Well, it calculates this quantity. What is this quantity? Does this look familiar to anybody? It's Bayes, right? It's just a Bayes rule. So this is your prior belief, prior distribution on theta. This is your new signal, and this is just Bayes rule that you probably have all seen in, undergrad probability for updating your belief over that signal, right? So this is just saying calculate a new belief on theta given your new signal. And then what do? I just average that with the beliefs on theta from my neighbors, right? So I incorporate the signal by using Bayes rule, very natural, and then I just average with my neighbors. Again, supernatural. Okay, then log linear. This is called a linear update rule because you're just taking linear combinations, linear averaging. Log linear is also very similar. If I were to take, it looks complicated. If I were to take the log on the top, I get weighted average again because the omega ij will come to the bottom. Okay, turns out this is a little bit faster. But at the end of the day, these are all average. Okay. So under what conditions will these averaging type approaches work? It turns out under some pretty basic conditions, it'll guarantee that the agents learn the truth. What are these conditions? The first is global identifiability. What this says is that for every pair of hypotheses, somebody in the network can tell those hypotheses apart, right? Somebody has to be able to say, these two hypotheses are different from the signals that I can get. If there's a pair of signals that nobody can distinguish, then everybody's equally confused about those two signals, okay? Okay, so you can see that this is sort of a mild condition. It turns out it's not strictly necessary, but I won't go into it. Condition on network structure, there's a path between every pair of nodes. Information has to be able to flow, so no big deal either. And conditions on priors, for every possible hypothesis and every agent, everybody starts out assuming it's possible, right? If you woke up today and said 0% chance the earth is round, what am I going to do, right? Anything I give you, you're not going to update that, right? So you have to believe at least even 1%. Just give me 1% and this algorithm will work, okay? Okay, so the key question is, I gave you those averaging algorithms. I gave you these general conditions. It turns out under these conditions, they work. Question is averaging the right way to go, right? Again, everybody has a natural tendency to average. Is averaging the right way to go? Well, since I'm asking this question, probably the answer is going to be no, right? Why else would I be asking this question? Okay, so here's where I think some of the key insights come in, right? Which is basically step back a little bit and think about what are we doing in these networks? And one question would be, what can each agent do on its own, right? You should be self-sufficient. Like, don't talk to other people and get help. You should learn to do stuff on your own. Only when you can't do something on your own should you rely on other people. Okay, so what could each agent do on its own? Well, if it wasn't going to listen to anybody else, what would it do? Well, it would just use Bayes rule, right? Repeatedly to continually update its beliefs, its probability distribution over the hypothesis. This is Bayes rule, okay? And so there's certain things you can prove about Bayes rule. It comes just from the insights we've seen before. One is that, okay, the signals are being generated by this true signal theta star, this true hypothesis theta star. If you run Bayes rule on the signals that are generated, if a certain hypothesis theta is not observationally equivalent to theta star, what does that mean? The distribution of signals generated by that is different than what is actually being generated. then your belief on that theta will go to zero. Just like your belief on, theta 2 being true started to go down after you saw that string of heads. Your belief on these hypotheses that are different from theta star observationally will go to zero. However, theta is observationally equivalent to theta star, right? Theta 1 and theta 3 in that example, then we can never tell them apart. And that belief is going to be bounded away from zero, right? You can easily prove this. So the key insight here is that each agent, without talking to anybody else, can determine a set of states that cannot be true based purely on its own signals. It may not be able to figure out what is true, but it can start to rule out states which probably are not going to be true, right? In that case, we have theta 2. So here's that exact same example back, right? So we have that same signal structure under theta 1 and theta 3. We see 3/4, 1/4. Under theta 2, we see 1/2, 1/2. Suppose theta 1 is the true state. It's going to be generating the signals. You run Bayes' rule, and you can see your belief on theta 2 may go up at the beginning, just like it did for us. But over time, right, the law of large numbers kicks in, and you're going to start having lower and lower belief on this. Theta 1 and theta 3 are going to be indistinguishable here. So the key thing is, on its own, each agent can start to quote unquote rule out certain states, but there are other states it can't distinguish. So that's where now it has to say, well, I can't do this on my own. How can I get the rest of the network to help me? Okay, so if each agent runs a local Bayes estimator, it can asymptotically determine that some set of hypotheses are false. The true hypothesis will never be eliminated by any agent, right? Because that true hypothesis is going to be consistent with the signals every agent is seeing. So how do we leverage this? How do we leverage the fact that somebody over here knows that theta 2 is false? And over here, they know that theta 5 is false. And over there, they know that theta 7 is false. So how do I get to merge theta 2 is false with theta 5 is false with theta 7 is false to figure out what's left? What I need is a way for low beliefs to propagate throughout the network. You telling me it's false means you have a belief close to zero. So I want zero to fly like fire through that network, right? So here's the key idea that each agent maintains two belief vectors. A local belief based purely on local signals, right? This is just using Bayes' rule. Don't talk to anybody else. Don't corrupt your local information with other pieces of information. This is just for you to start figuring out what stuff is false. And then an actual belief, or sometimes we call a network belief, that merges beliefs from neighbors from your neighbors with the local beliefs. Okay. And the key idea is that when you're updating your belief on theta, do not average. Take the minimum of your neighbor's values. Because if one of your neighbors is saying that's false, that's probably because they know what they're talking about, and you should rule that out. It's like saying, I don't know anything about nuclear physics. And so I think, world is flat versus world is round 50-50. And somebody else says, you don't have to be a nuclear physicist to know the world is round, but I'm pretty sure the world is round. We're like, let's agree to disagree. I'll take it to 25%. No, you should be like, you know what you're talking about. It's going to be zero, right? That the world is flat. So that's exactly this idea. Averaging is like, agree to disagree. Let's get a little bit closer. This is basically saying, you're the expert. I'm going to listen to you. So this is the rule, right? For each hypothesis, listen to the neighbor that has the lowest beliefs on that hypothesis. Is that like embarrassingly simple? That should be clear, right? Okay. Yes.
It only has access to its own set of hypotheses, right? Like there's three in the example we gave.
Yeah, the set of hypotheses is common to all agents. Yeah, everybody knows the set of possible things that could be true, but the signals are different. Yeah, the signal structures and the signal. So mathematical updates are exactly, I'm just writing down the math for this, right? So essentially, this is the local Bayesian update that each agent follows, right? Using just its local signals, not talking to anybody else. This is how it merges information with its neighbors. Looks complicated, but all it's doing is for each theta, it's looking at its local belief here. This is its local belief from here. It's taking its neighbor's values and it's taking the smallest over all of those. And then this is just a normalization to make sure everything sums to one in a belief vector. Okay. Under what conditions will this work? It seems intuitive. Well, it's exactly the same conditions as before. Global identifiability, strong connectivity, non-zero priors and hypotheses, guarantees learning in the system, right? Much simpler algorithm, hopefully intuitively. And let's look, again, my impressive kind of notation here. All this is saying is the following. Mu IT on theta, this is the belief on some false hypothesis theta. I would like this to go to zero. How quickly does this go to zero? Well, if I take the log of it, and I do -1/t, that exponent. So what does it say? Mu it decays exponentially fast, right? At a rate, meaning the coefficient in front of the t is given by this value. What is this value? This is just saying for each theta, look at the node in the network that is best able to distinguish between that false hypothesis and the true hypothesis. And that node is going to drive everybody else's beliefs to zero. Again, it makes sense. If you're able to quickly eliminate a hypothesis based on your signals, your beliefs are going to go to zero at a certain rate, which means because your neighbors are taking the minimum of the beliefs, they're going to adopt your value. That's going to fly through the network, right? So everybody gets the benefit from the best guy in the network, right? And this is basically in contrast to existing approaches where, the rate of learning is diluted by everybody. So everybody wants to have a sort of a say into learning. So here's a simple simulation example. So you got a bunch of agents that are, monitoring a certain environment. There's a target in one of these cells, okay, cell 1, cell 2, cell 3, or cell 4, or cell hypothesis 0 is that there's no target in the environment. So these sensors, these agents want to figure out which of those hypotheses is true. Is there no target, or is the target in one of these 4 cells, okay? And so each of these agents is going to be flying around. They're going to be getting signals from the environment. And if you run these 3 algorithms that I mentioned, so red is our algorithm, green is the linear averaging, blue is the log linear averaging. These are the beliefs of 3 different agents on the truth, right? The truth is that the target's in cell 2. Going to 1 is good. That means they've learned the truth. And you can see our algorithm, right, is learning faster than these existing algorithms, just as we predicted. Okay, this applies to distributed classification as well, right? So I'm just gonna, basically I talked about likelihood functions, but you can imagine you're trying to classify a certain object, right? Is it a cat? Is it a dog? Is it an airplane? What kind of drone is it, etc. You could train classifiers for this, right? You can maybe random forest or something. And imagine you've got a network now where different nodes have classifiers that are trained on only subsets of these things. So for example, Waterloo may only be able to tell apart cars and trucks. And maybe you can only tell apart different kinds of airplanes. So then you can tell apart different kinds of birds. Could we work together, despite the fact that no individual can tell apart all hypotheses, by leveraging this cooperative hypothesis testing framework to be able to eliminate, and eliminate false hypotheses, learn the truth? Exactly the same ideas go through in that setting as well. Okay, so I'll skip shot. Okay, so basically what I told you is from now on, every day you wake up and you talk to your friends, and you get the one who has the lowest value on a certain thing, and you take their value and you live your life happily, right? Would you do that? Why wouldn't you do that? Exactly, right? And so if you're like, yeah, that guy probably knows what he's talking about. All right, the world's flat. All right, and I go tell my friends, they're gonna be like, oh, that guy probably knows what he's talking about. Well, problems. Okay, so if everybody was legitimately working like this and the assumptions were true, everybody would learn. But not everybody's going to do that. And so you can imagine the easy way to corrupt this algorithm is for some node in this network to just be like belief of 0 on the truth. Okay, because I don't want you to find out the target in cell 2. So in this case, that's what happens, right? So agent 5 basically says, I don't, these guys are close to figuring out that the target is there. I've been sent into this network to prevent them from finding that out. I'm going to set my value to 0 on the truth. And you can see everybody else sets their values to 0 rapidly, right? So easily corrupted. Okay, and these other algorithms are, it's the same problem. Okay, so how do we think about resilience to these bad guys in these settings? Okay, so no existing work at the time that we did this dealt with this resilience in this case. There's one paper that looked at it, but it was very computationally expensive. So again, we're going to look at Byzantine models, F local adversaries, right? So really, really, tough setting. But same deal, right? So let's go back to our algorithm. Local beliefs, they don't talk to anybody else. So that doesn't change, right? It's just local Bayesian updates. You should trust yourself, hopefully. So you're going to do this. For incorporating information from your neighbors, if I have at least 2f+1 neighbors, if I don't have 2f+1 neighbors, this is a typo, this should be less than or equal to, I'm just going to stick to my local beliefs. I don't trust anybody, okay? But if I have enough neighbors, then what I'm going to do is I'm going to grab all my neighbors' opinions. I'm going to filter out highest F, lowest F, and then just take the minimum of the rest. So exactly the same process as before. And then you can prove under certain conditions that this will converge. So remember, when we were filtering in the consensus setting, we needed that robustness property, right, to make sure information would cut in. There's something extra that is needed in this setup. So in the consensus and optimization setting, everybody was equally informative. Your opinion mattered as much as mine. In this setting, it's different. Certain nodes have important information and certain nodes don't, right? If you're able to tell apart a certain pair of hypotheses and I'm not, everybody should make sure they have access to your information and shouldn't care about mine. So in this case, we need two types of redundancy. Information redundancy, which basically captures the idea that is there a sufficient number of nodes that are gathering the required information? Because if they're not, the bad guys can just compromise all those informative nodes, right? If there's only one person in the network that can tell apart a pair of hypotheses, the bad guy compromises that node, nobody will ever be able to distinguish between those pair of hypotheses. So you need information redundancy, but you also need communication redundancy. It's not enough to say, hey, there's enough people that can distinguish a pair of hypotheses, because that information has to flow through the network to the rest of the nodes. So then if the bad guy compromises some bottleneck in the network, that information still can't flow to other nodes in the network. So you need both of these. And that distinguishes this from consensus and optimization type problems that we've looked at in the past. So it turns out you can come up with a different condition, which we call strong 2f+1 robustness, in order to be able to capture this idea that there's informative nodes. Okay, so let me just introduce that really fast. It's super basic, exactly the same as before. So suppose you have a graph, you have a set of source nodes, right? These are nodes that are getting important information. If I give you a subset of nodes, I'm gonna still use that R reachable condition. But now I want to talk about graphs being strongly R robust with respect to a given source set. And so we say a graph is strongly R robust with respect to the source set S if every non-empty subset of V minus S is R reachable. What does this mean? Okay, let's do an example. I give you this graph, that's the source set. Let's say these are the sets of nodes that are getting information from outside. I check every subset of the remaining nodes and I see if every subset is R reachable. So for example, this subset is 3 reachable. It's got 3 incoming edges from outside. This set is 3 reachable. It's got 3 edges from outside, right? This set is 3 reachable. So I check every possible subset, and if they all are 3 reachable, this graph is 3 strongly robust, or strongly 3 robust with respect to the source set. Definition clear? Okay, so this ends up being the critical condition for capturing both information redundancy and communication redundancy. It ends up blending both of those things because you are now checking redundancy with respect to the source set. And as long as the graph is strongly 2f+1 robust, so you've got non-zero priors on the hypotheses, everybody will learn despite the actions of F local Byzantine adversaries. Again, very simple idea, this condition. Unlike the R robustness condition, it turns out, maybe surprisingly, that this property can be checked in polynomial time. There's a very simple algorithm to be able to certify a graph having this property. Okay, so this is just a, proof via simulation that this will work, right? So essentially the same setup as before. Node 5 is the bad guy, sets its belief to 0 at that time. At that point, before the filtering, everybody had, dropped to 0. Here, these algorithms are already dropping to 0, but our algorithm soldiers on. Okay. Great. So let me just summarize the distributed hypothesis testing idea. So the key insight here was that, averaging is good, but you could do better if you have settings where certain nodes are more informative than others. Okay, and so we showed this nice new rule that talks about a min rule rather than an averaging rule, and we can extend that to Byzantine adversaries. And there's all sorts of extensions. You could do event triggered, quantized communication. It turns out that there's an even dumber and better algorithm for this problem that I didn't talk about. Okay, and so you can actually learn in finite time. It's not even an asymptotic rate. Okay, so don't work on this problem. It's the conclusion. So key takeaways from the entire talk. Networks are a double-edged sword. Okay, so the point of networks is for nodes to be able to work together, to be able to learn things from each other, right? So things that some people know can spread to other people that don't know, so they can all get better. But there's also then the possibility for bad guys in the network to spread misinformation and corrupt everybody. So that's why there's two edges to this sword, right? And off-the-shelf distributed algorithms that don't account for this can be easily compromised in these settings. Furthermore, if you're going to say I'm working on resilience or I'm creating a resilient algorithm, you better define what you mean by resilience, right? What are the fault models? What's the objective? What's the number of adversaries, etc.? And the redundancy properties are going to depend on these things that you achieve, right? So what do you need from the network is going to depend on what you're trying to achieve. And so all robustness is this new kind of graph property that facilitates these scalable distributed algorithms. Finally, when the network has heterogeneous sources of information, you need two kinds of redundancy: information redundancy and communication redundancy. Okay, both of those have to work together. New metrics, the strong robustness play a role. And then if you do have experts in your network, averaging will work, but may not be the best, right? So just kind of a cautionary tale to take away. Think about better ways to do things if you can. And with that, I'll stop. Thank you.
I'll look forward to a few questions from the audience.
I have two questions here. One is, with hypothesis testing, could your data be continuous?
Great question. Yeah, you can.
Okay.
These kinds of algorithms will suffer because essentially what you want to do is, when you're doing that Bayesian update, what does it mean to throw away or adopt the lowest belief? Your probability distribution, the way you represent that is going to be a giant mess at that point, right? And so how do you think about representing those kinds of things in continuous spaces? There's a lot trickier. There is work on it. Okay, yeah.
My second question is, how does it work if your hypotheses are varying with time?
Excellent question. So then it's a tracking problem. Now, if it is a discrete set of hypotheses and they're varying with time, you've got some model for it. That's sort of a Markov decision process. If it's a continuous set, a continuous state space, and it's varying, let's say, in a linear system fashion, I didn't talk about it here, then it essentially becomes a distributed observer problem. Same insights hold. So distributed observer, for people who've taken estimation theory or control systems, is basically you build an estimator that mimics the behavior of the dynamics, and then you add a correction term to it. Naturally, people had looked at this and said average. But then if you average measurements or estimates, for example, it turns out you have very strong conditions that show up on the dynamics of the system that you can track, because essentially you get this information propagating through the system. Estimation errors also propagate through the system. So when I'm averaging, I may be sort of amplifying errors if the dynamics themselves aren't sufficiently fast or stable. So then it turns out actually averaging is not the right way to go. You should try and identify pieces of the state that different people can estimate based on their local measurements and allow information from them to flow. And you kind of say, you estimate velocity, you estimate position. I'm going to grab your position estimate and your velocity estimate and put those together. So yeah, I can point you to papers on that.
Well, I would appreciate it.
Sure, absolutely. Yeah, great questions.
More about the malicious